Okay, we start our class today. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Yeah, I'm sorry. I cannot perform the class yesterday. Sorry, last week. I hope today, yeah, our first meeting. Yeah. Also, we have only 2 meetings, and to be honest, it's difficult for me to explain in mathematics context. Yeah. This course, but only in 2 meetings. Yeah, actually, our class in mathematics for modeling, it is delivered in 1 semester actually. Yeah, of course that I only choose some materials, some topics which I think are very relevant. Yeah, very relevant and very contextual in biology. And then, to be honest, I haven't prepared yet the slide by myself. So I just pick up someone slides, which I think is very good. Yeah, it's very good, and it's very relevant. Yeah, to our class today. Okay, I think I have to show the link and then the website that you can access. Wait a minute. I have to find the link. Wait. So wait. Okay, so wait. Okay, this is the website. I think good website for you to explore the materials here related in our lecture. Yeah. So I have been assigned from Mr. Adrian and Mr. Wilson to give what do we call that? The mathematical ideas, yeah, the mathematical technique related to this course. So you can access this website, yeah, and then choose the teaching menu here. Is everyone can see my share screen here, the website?
Yeah, I see, sir.
Okay. Okay, I think I have to give you the link, yeah, in the menu, chat menu, yeah. Okay. Okay, you can choose this menu, the teaching menu, and then click the past courses, yeah, and then click this one, yeah, population dynamics. I will use this slide, yeah, introduction, exponential growth, and logistic growth, yeah. You can download it by yourself, or you can also download it in our e-learning, yeah. I have uploaded the slides into the e-learning. Okay. And if you can see this website, yeah, this is actually the Department of Biological Sciences, yeah, at Simon Fraser University. So this is the biology, yeah, biological biology department actually, yeah. But the materials here is related with the mathematics, yeah. So I think it is very relevant for you to access the website because this is actually the biological sciences department, yeah. Okay, so I will start the first topic. Okay, so we just use this slide, yeah, from this guy. uh, yeah, about models, yeah, but uh, but the models is not about this, yeah. It's not about the models. Someone, yeah, someone pictures, no, or someone performance, no, yeah. We talk about models in terms of mathematics. Okay, there are two major classes of models, yeah, in mathematics, yeah. So the first one is statistical models, okay, and I think you have obtained the statistical course, yeah, in biology. Have you obtained this statistical models in biology? I think it is a compulsory course right now, statistics in biology. Have you obtained the course? Hello?
Yes, sir.
Biostatistics, yeah. I think biostatistics, yeah.
Yes, sir.
Biostatistics,
Bio
biology.
statistic
Yeah. Have
in
you obtained that? Have you obtained that course? Have you
Yes,
got?
sir.
Yeah. Okay. So maybe you know uh, terminology of regression. I think, yeah. Regressions is that taught in the lecture, in statistical lecture. Regression. Do you remember, or there is no topics about regressions in the course, in the biostatistics course? Hello? Do you understand what I'm saying?
uh, yes, sir.
Yeah, I
I'm
just
sorry,
want
sir.
to confirm. I
Yeah.
just wanted to confirm whether you have obtained, whether you have got uh, the materials, the topics in statistics. Yeah. So one of them actually, yeah, is about regression. yeah, regresi, yeah, regresi, yeah. So in in statistical models, it depends on data. Yeah? It depends on data. So the models built, belum lagi. Yang ini sudah ini. Generated by statistic. It depends on data. Yeah. So that's why we call this as data dependent models. So it requires data in order to test hypotheses about the empirical world. Yeah. So someone has hypothesis about the empirical world, yeah, and then we build the model, yeah, the data dependent models, to test whether this hypothesis can be accepted or rejected. That is statistical models. And the second one is mathematical models. Yeah, mathematical models. This model is not depend on does not depend on the data. Yeah. So this why that's why this is called data independent models. To usually, yeah, generate the empirically testable hypothesis. So this is the quite difference, yeah. So statistical models require data to test our hypothesis, but in mathematical models, we make the models, yeah, to generate the hypothesis. Yeah. And of course, that hypothesis that we generate from the models, it can be tested again, yeah, using statistical tools. But these two models actually can intersect, yeah, can intersect. So this is not black and white concept, yeah, something that can be interchanged, yeah, each other. Yeah. For example, if you use or if you study or if you generate the mathematical models, yeah, you have to know the parameters value, yeah, the parameters values. How to generate the parameters? Yeah, we use the statistical models, yeah, and also in other directions, yeah. So statistical model also need the mathematical models to make some insight, yeah, what models that we have, we can try to make it. Okay, but right now our focus is on the mathematical models, yeah, so not statistical models. The statistical models, maybe you know about the what do you call the PKM creativity program of a student creativity program, yeah. Last year, yeah, one student from mathematics, and also there is one student from biology, yeah, won the gold medals in presentations in poster. So what they did actually is statistical models. But right now in this class, we will discuss about mathematical models. So even if we haven't if we don't have a data, we can still make the models to describe some phenomena in this nature. Okay. In mathematical models, we also can again split into two categories. The first one is applied models, and the second one is the theoretical models. So what is the difference between them? The applied models actually, in brief explanations, we can say that this is just for the one particular case. So we build the model to provide insight into specific empirical systems. So this works, this model works only for one particular case, one particular system. But in theoretical models, can be used to general cases, actually. So we can use this model, the theoretical model, to be implemented in many cases. Of course, the cases should be relevant. Should be relevant to the models itself. For example, I think you hear this. You have known this, I think, and I think Pak Adrian also mentioned about this. Predator prey models. Or prey predator models. Mangsa pemangsa. So the model itself is general models. And we can implement it, we can apply it into many cases, into several, into many cases that related to the prey predator cases. For example, we can use, the predator, for example, wolf. Wolf, is that correct? Wolf, wolf as a predators, and then deers, deers as a prey. So for that case, we can use this model. Or maybe we also can use other cases. Can you mention what is the example of the predator and prey in this nature? For example, tiger, tiger and what? Tiger and some species, some animals. So what we discuss in this class is about the theoretical models. So from the beginning, we only focus on mathematical models. In mathematical models, we only focus on theoretical models. However, this model actually, theoretical model actually lack the realism to be accurately model specific systems, because they are generated under assumptions, under many assumptions that, of course, that it is very hard to make it realistic, to make it relevant to the nature phenomena. But it is not ideal. However, we can use it, under the limitation, under the limitation of our assumptions. Okay, if you have a question, just please freely to mention, directly, not waiting for me to open a question session. So if you have question, just raise your hand. and then say it directly. Okay, so historically, mathematician and statistician did everything by hand. If you have ever watched some movies, it is very nice to see the skins someone, mathematician or statistician, write down something, equations, in the whiteboard or in the blackboard. But today, we are fortunate to live in the age of computers. So it is no longer necessary to be mathematician to analyze fairly sophisticated models. So we will be helped by computers, by applications, by software, to calculate, to solve, or many things, many jobs, that if we do it by hand, of course that it will be difficult, to do it. Or maybe it can be done, but maybe take a long time, But by computers it can be effectively, and efficient, and very quickly to get the solutions, to calculate something, to visualize the results in graphics, in curves and blah blah blah. So we can use these computers. Also, for some cases, something that we have to check it, we have to test it, by hand, for some cases, but in general, we can use the computers. Okay, for example, I think you have been introduced by R, by R, C, C++, and etc. Is that correct? Have you been introduced? Have you know about this? The R language, bahasa bahasa R. Have you known this?
Maybe R Studio, sir. In biology, have application R Studio, sir. Maybe that.
That's the same thing. R. R. In mathematics we use MATLAB actually. But I think basically the language still the same. We just have to know about or familiar about the language, about the code. Okay. This is just the introduction, for the models. So mathematics permeates biology. What something that biology, from the perspective of biology, for example, we want to study about the models in nature, phenomena. Of course, we have to know about the biological concept, biological theories, and then that concept is brought to mathematics, and then it will be explained, and then transfer it into some equations, some mathematical equations. But the equations itself has to have a meaning, has to have a biological meaning, in the equations. So that's why mathematics permeates biology, Whether it is simple calculations, simple models, or sophisticated models, of course that we still need biological concept, biological theory into the models. Okay, for example, there is a very reputed journal, international journal, Nature. I think you know this, Nature or Science journal. This is very good journal, international journal. Several of the biological articles, in the journal are likely to be based on research involving mathematical models. So what they explained is about biological phenomena, but the research itself actually a lot of mathematics calculations, that they present in the paper. This is one good example, So the paper was written by Phillips, in 1996. So actually, he discussed about the reduction of HIV concentration during acute infections, independence from a specific immune response. But you can see, just googling, this paper, you can download it free. You can get the PDF of this paper. You can see that the paper itself is a lot of mathematical calculations itself, because what he explains, what he studied, what he presented in the paper is about mathematical models, in the context of this phenomena, about the HIV concentration, during acute infection. This is very nice paper actually, so maybe this is just the quick explanation, quick review, review the mathematical model in the paper, So who's the name? The authors, Phillips, Phillips. Okay, so Phillips in the paper generate 4 equations, 4 differential equations in mathematics, to explain the HIV reductions, in the concentrations. We will not discuss about this actually. This is just one example, where the biological research, can be studied, in mathematics. A lot of mathematics in this paper. Okay, I just leave it. It's not what we want to discuss actually. Okay, so what is the population dynamics actually? Because in this course we discuss also about the population, right? Populations, some species, right? Yeah, populations, modeling of biodiversity. Yeah, I think. Yeah, so it is related with the populations of specific or particular species. Yeah. So in general, we call it as population dynamics. Yeah, it can be human. Yeah, it can be uh, many species. Yeah, can be the number of tigers, the number of uh, wolves. Yeah, or maybe the number of cells itself. Yeah, the micro in micro size. Yeah, we can also uh, find the populations. Yeah. So what is the population dynamics actually? You could think of it as population bookkeeping. Ya, jadi pembukuan, ya, pembukuan populasi. Ya. So for example, in the first day, the population of particular birds, yeah, yeah, I don't know what is the species, yeah. We can record it, yeah. One the first day, or maybe not days, yeah, maybe in months, I think, yeah. The first month, this one, yeah, the number of populations. The second month, that one, yeah, or maybe in year, yeah. It also be possible to record it in by year, yeah. The number of Indonesian population, for example, yeah. This year, the next year, and so on, yeah. So the population dynamics is used, yeah, to investigate how populations change. Yeah. Change, it can be increasing or decreasing, or maybe relatively stable, yeah, constant, yeah, over time. Yeah. So basically, yeah, the factors that can make a change in the populations, yeah, are these factors actually, yeah. The number of births, yeah, and then the number of deaths, yeah, the number of immigrants, and the number of emigrants, yeah. Number of births will increase the populations, yeah, of course. The deaths will decrease the populations, yeah. The immigrants will increase populations, and the emigrants will decrease the populations, yeah. So the blue one, the component or the factors that can make the populations increase, and the red one make the population decrease. Yeah. So this is just the basic ideas. Yeah. How can population change? What factors? Yeah. What factors that can be uh, uh, changed? Yeah, the population itself. So in the simple way, yeah, we can make the equations. Yeah, this is very simple. Yeah. So n is the number of populations. Yeah, yeah, some species. Yeah, at time t+1. Yeah? So the number of population at time t+1. Of course, that we have to know about what is the number of populations in time t. Yeah, for example. Yeah, t can be days, months, yeah, years, yeah. And then of course that we have to add it by the number of birds. Okay? Birds, yeah. And then minus the number of deaths, and then the number of immigrants, and then minus number of immigrants, yeah. So this is just simple equations, yeah. Do you understand about this? Yeah? Can you follow this? Do you understand why we can make like this?
I wanna ask something, sir.
Yeah.
What is again yang N, sir?
The number of population. Yeah,
Oh,
the
alright.
number of populations. Yeah, for example, if you want to focus or investigate the number of wolves, for example, yeah, the number of cats in your area, yeah, in your maybe cats is not really maybe the number of what mouse. I don't know. Yeah. So the next one we can calculate it. Yeah. Of course that today, yeah, right now, plus yeah, the birds, yeah, the deaths, yeah, immigrants and immigrant. Immigrant is the populations comes to our place, yeah, comes to our area. Immigrants, the species go out, yeah, from our area. Yeah, can you understand this?
I wanna ask again, sir.
Yeah.
In the left side is N T plus 1 and the right side is N T. What the difference about the two of that, sir?
Yeah, T plus 1 means the next time, yeah. So at time T, yeah. For example, today, yeah. So T plus 1 will be the next day, yeah, tomorrow. So the number of person tomorrow is equal to the number of person today, yeah, plus the number of births today minus the number of deaths today plus number of migrants today and minus number of immigrants today. Yeah. Yeah. If we
Okay.
if you use it T is tomorrow, yeah, for example. So T plus 1 will be the next day, yeah. The next 2 days, yeah. Yeah, so this is just the simple, yeah, simple equations. Yeah, T can be days, yeah, in days or in months, in year, yeah. So if we want to calculate this year, so T plus 1 means the next year, yeah. Okay. So this equation will form the basis for the first model we will investigate in this class. Yeah. Okay. So this is the introduction for the population dynamics. Yeah. Now we will move on the discussion about the one model, mathematical model in dynamics, yeah, in population dynamics, which is very fundamental, yeah, very simple model, yeah. This is called the exponential growth model. Have you seen the new slide
I see,
about the
sir.
exponential growth? Hmm?
I can see. Oh, sir. This stop screen, sir.
Okay.
I see,
What
sir.
about this? Okay.
I see, sir.
Yeah. So, wait a minute. I have to open the zoom, another zoom. Okay. Okay, this is the example of the real phenomena, yeah, real case. So in 1937, two cocks and six hen pigeons, yeah. I don't know what kind of species this. I I I try to translate in Google. Pigeon is burung pegar, yeah. Is that correct? Burung pegar. Yeah, burung pegar. I don't know what. I think the color one is the cocks, yeah. And then the, yeah, because in birds, what is the English jantan? I forgot. The male, yeah, the male, yeah. Is that correct? For birds, is that correct? It's also the male, yeah, and female, yeah, female for betina. For example, this is for the male, and then this is one for the female, yeah. So there are two cocks, yeah, and six hen were introduced onto an island off the coast of Washington, yeah. So we can say that the island, yeah, will make the limitation for the birds, yeah, to go outside, or some or in vice versa, maybe other birds come inside, yeah, into the island, yeah. So that's why we can record, yeah, we can write down the number of populations of these birds, yeah. We can investigate, yeah. We can what we call that, we can make a census, yeah, of these birds, yeah. So over the next 5 years, yeah, the result is this one, yeah. So based on the records of the population of this species, yeah, we know that the curve, yeah, the data itself experience the exponential growth, yeah. So it grows exponentially, yeah, exponentially. Yeah, it means that in mathematics, yeah, in mathematics we can wait. We can actually, yeah, for example, something a constant times sorry, to the power of t, yeah. This is exponential, yeah, exponential function, yeah, exponent function actually, yeah, exponent function, yeah. So alpha can be replaced by a number, yeah, by a number. Okay, so that is the exponential function actually, yeah. It is a difference with the power function, yeah. So the power function, we make it is like this, yeah. T, this is power function, fungsi berpangkat, ya. berpangkat. Yeah, for example, if you have 2 squared, for example, yeah. So we know that the graph is something like this, yeah. Yeah. Ya, ini 40 start from 0, for example. So that's why I just draw the graph, the curve starting from 0, yeah. But in this case, what we want to discuss is about this one, yeah, exponential function. So the t is the power, yeah. Well, in the power function, the number, yeah, we want to make it to the this is difficult to say. So the power function is the t. What is the power of t? Yeah, and this one what the t itself is a power. Yeah, pangkat. Yeah, pangkat. The power is pangkat. Yeah. Okay. Can you make a difference between the exponential function and the power function? Yeah. In popular in the popular function, yeah, it is related with e, yeah. So our alpha is e here, yeah. So we will have e to the power of t, yeah. This is the popular expressions, for example, yeah, for exponential functions. But in general, actually, this is just number, yeah, number. Okay. So if we want to draw this curve, yeah, of course that we will have something like increasing, and then the increasing graph, yeah, we want to know, yeah, for example, yeah, this is just example, yeah. So what is alpha such that the number of this population can be approximated, yeah, by the models, yeah. Oh yeah, I think I have to add this by something, yeah, by something and not I think, yeah. Oh, sorry, yeah, and not is initial number of populations, yeah. For example, and not here is 2 plus 6, yeah. So it will be deep. It will be uh, 8, yeah. 8 birds, yeah, in the beginning. Yeah. Okay. Okay, so we will find what is alpha in this case, but we have to explain something, yeah, before this. Any questions so far? No. Okay. Okay. Let us recall, yeah, recall what we have explained before. So the fundamental aspects, yeah, fundamental factors that can influence or can change the populations, yeah, are these four factors, yeah, number of births, number of deaths, number of immigrants, and number of immigrants, yeah. Yeah, so we can write like this, yeah. It's just the same with the previous one, yeah. Now if we write like this, yeah, so actually this is in the discrete case, yeah, actually, yeah. because we have, for example, in days, yeah, we only have today, for example, and then the next day, yeah, next 2 days, the next 3 days, and etc. Yeah, and so on. And because these equations depends on the previous, yeah, previous number, previous quantity, so we say it, or we call it as a recursion equation. Yeah. So the equation itself, the number of population can be obtained if we know, yeah, if we know the number of populations in the previous days, for example, yeah, in the previous months, on the previous years, for example. So this is recursion equations. In contrast, the HIV, yeah, example that we have discussed before, it is continuous model. Yeah, so the model is in the continuous time. So that's what we call it as a differential equations. Yeah. So this is the recursion equations. Yeah, and this is the differential equations. I don't know whether you have you obtained the mathematics course in the first year.
Yes, sir.
Yeah. Have you studied about the differential, yeah, derivatives, turunan, turunan? Have you studied about this? About the derivative or differential turunan in our language?
Yes, sir.
Yeah. Okay. So this is the differential expressions. Yeah. This term. Yeah. Suku ini. Yeah. This term refers to differential expressions. Yeah. So that's why we call it as a differential equations. Yeah, because we have a equal sign here. So if you have something that there is an equal sign, yeah, so it's called equations. Yeah, equations. And if the terms contains differential function, yeah, so it is called differential equations. Yeah. Okay. Okay, how you analyze a model and the behavior of the model, both, yeah, discrete or in continue. Yeah, we will discuss it. Yeah, so we will discuss about the discrete first, and then we'll continue in the continuous case, in continuous case after that. Okay. Besides the 4 components that we have mentioned before, yeah, the number of births and then deaths, immigrants and emigrants. Actually, we also have additional factors, yeah, that can influence it, that can change the population as well. Yeah. Yeah. For example, food, yeah, or resource availability. Yeah. If some species lack of food, yeah, in interval of time, yeah, of course that it will give effect to the decreasing of its populations. Yeah. Or weather, yeah, weather is not in good conditions, yeah, maybe make some species cannot survive, yeah, for example. Competitions, yeah, competitions among the species, yeah, So, for example, in the groups of the tigers, for example, yeah, they also compete by themselves, yeah. Who will be the winner, yeah, for example, to obtain some prey, for example, yeah. The tigers maybe fight, yeah, each other. So of course that it will also can reduce their populations, yeah. Or predations, yeah. Predations of for some species, other species, yeah, that can make the populations reduce, yeah, because that will be its food, yeah. Example, wolves, yeah, wolves. It's deer, for example, yeah. So the wolves can reduce the populations of the deers, yeah. The tigers can reduce the population of yeah, some species, yeah. Or disease, yeah. Disease also can change the populations, yeah. For example, today, yeah, the COVID-19, yeah, many people died, yeah, because the COVID-19. Yeah, of course, that will be give the effect to the populations change. Okay, we will include some factors, yeah. So if we want to include all of them, of course that we will have complicated models, yeah, actually. So right now, let's start with the simplest models describing population size. Yeah. They are exponential growth, yeah, and logistic growth. Yeah. So there are two fundamental models, yeah, in dynamic populations: exponential growth and logistic growth. Yeah. And these two models assume these items, yeah. So constant food and resource availability. Yeah. So there will be no issue, yeah. There will be no problem in the food, yeah, in the logistic resource, yeah. It is always available, yeah, over time, yeah. This is our assumptions, yeah. Of course, that is very simple, yeah. And also we can assume a constant environment, yeah. There is no change in the weather. There's no change in the, for example, supply of the water, yeah. Clean water is, yeah, etc. Yeah. Or the air, yeah. The air is still fresh and something like that, yeah. So there is no change in the environment, yeah, that can change the populations. Or we can say that it is a constant environment. And then we also can assume no interactions, yeah, with other species, yeah. No interaction with other species, yeah, with the predators, for example, yeah, that can make the species reduce, yeah, no interaction. So this is just one species. So exponential growth and logistic growth is just for one species, yeah. There is no interactions with other species. And also there is no disease, yeah, no disease, yeah. Of course, that is very simple, right? Yeah. In the real life, of course, that we will not have these items, yeah. No disease, yeah. Constant environment. Wow, this is wonderful life, actually. Yeah, but it's okay, yeah. We can start with these assumptions, yeah. Then we can see what we will have, what we will obtain, yeah, from the model by using these assumptions. And then what about competitions? Yeah, competitions. So for the exponential models, we assume there is no competitions, yeah, among the members of the species, while the logistic growth, yeah, it will include the competitions, yeah, competitions, yeah. So of course that the real phenomena, yeah, in the real situations, of course that there will be a competitions, yeah, among members, yeah, even the animals, yeah, our species, yeah, our human, yeah, also make a competition, right? Competitions in getting something, yeah. Of course that in animals there is also competitions, yeah. This is the difference, yeah. The exponential models assumes no competitions. However, the logic model includes the competitions. So no competitions means density independent. Yeah, it not depends on the density. Yeah, on the number of population of a species. Yeah, while the logistic it depends on the density. Yeah, the more the populations, of course, that there will be a bigger chance, yeah, to make a competitions, yeah. It is can be accepted, yeah, the ideas. So if we leave just maybe one or two of for example our ourselves, yeah, in human populations. For example, we only have two members, yeah, or three members. Yeah, maybe the life is still well, yeah, going well. But if we have in a house, for example, 12, 12 members, yeah, of course that we can predict there will be competitions, yeah. So density independence means that it not depends on the populations, and then density dependent means it depends on the populations, yeah. So in the exponential model, we assume the no competitions, yeah, and the logistic model assumes there is competitions. Okay, both of this model, yeah, exponential and logistic growth, yeah, will be described, yeah, by equations that we will obtain. Yeah, we will discuss it today, whether in discrete or in continuous time. Yeah, can you follow until this point? Okay.
Yes, sir.
Okay, let us discuss about the modeling of exponential growth in discrete time. Yeah, recall our equations that we have discussed before. Yeah, we have this. Okay. Now, now we will have again simplifications. Yeah, there is no immigrations or emigrations. Yeah, so there is no one comes to our place, and there is no one move from our place. Yeah. If we assume this, of course, that we can make ET and IET is equal to 0. Yeah. Okay. So if ET and IT is equal to 0, we will have these equations. Yeah. Okay. Now, if we assume that each individual produces, yeah, if each individual can make a child, how can we say that? Have a baby, yeah, for example, yeah, a new one, on average, So let's say B offspring, yeah. So the newborn, yeah, the newborn of some species, let's say it is quantified by B, yeah. So how many offspring will be produced, yeah? On average, for example, B, yeah. And now we also have probability of death, yeah. Someone die or any species die with the probability D, yeah, for example, how many individuals will die. So we can replace BT, yeah, because BT is the number of birds, yeah. So we can replace the number of birds with B times NT, yeah, B times NT. So if NT is bigger, of course, that will produce more new individuals, yeah? Yeah. The bigger populations at time T, the bigger the newborn, yeah, will be produced. Yeah. Does that make sense? Yeah. For example, our country, yeah, Indonesia, or maybe India, yeah, India. Of course, that will have we will produce baby, yeah, in more number, yeah, because its populations is bigger, yeah. And dt, yeah, we can replace it by d times nt, yeah. Okay, so d is the probability, yeah. So if the probability of dying is big, yeah, of course that the people will decrease significantly, yeah. So it depends on the probability of d, yeah, probability of dying. So we replace bt by b times nt, and then replace dt by dnt, yeah. So we will have yeah, we can collect this, yeah, these two terms becomes these terms, yeah, b times d times nt, yeah. Can you follow this? Can you understand this? Okay. Now b minus d is a constant, yeah, because b and d also constant, yeah. So b minus d is a constant term referred to as the geometric rate of increase. Yeah, yeah. Increase means in general, yeah. Rate of increase doesn't mean it always increase, no, yeah. It's just it can be minus, yeah, of course, yeah. If minus will be decrease, right? But in general we call it rate of increase. Wait, yeah, I want to call some. Okay. So b minus d referred to as the geometric rate of increase. Yeah. So why we call this geometric? Yeah. I think you should remember with the geometric and arithmetic series. Direct arithmetic dan direct geometric. Please remember in senior high school mathematics. Yeah? So if you have arithmetic series, so we just add the number one by one. Yeah. But if you have a geometric series, we have to multiply it. Yeah, multiply it. So this case, b minus d is the geometric rate. Yeah, because we have to multiply it by n, and then for the next one we also have to multiply it by the next one. Yeah, so it will give the more and more number. Yeah, in terms of in terms of times. Okay, so b minus d, we denote it by r. Yeah, so we'll have just replace this b minus d by r. Yeah, and then we can collect these two terms, becomes this. Yeah, 1 plus r times n. Yeah, times n. Okay, because r is a constant. Yeah, so 1 plus r is also constant. So we can again, yeah, simplify the expressions of these equations by replacing 1 plus r with lambda. Yeah, for example. So we have nt plus 1 is equal to lambda times nt. Yeah. Okay, can you get it, all of you? What about you, Rian? Are you still in this class? Yeah, okay. Yeah, so from these expressions, yeah, from these equations, again, yeah, I review quickly. E and I, we set it by 0, yeah, because we assume there is no immigration and emigrations, and the rest will be re-expressed, yeah, rewritten, yeah, by these equations, yeah. Yeah. So what we have we call it before, yeah. This is recursions equations, yeah, for exponential growth, yeah, in discrete time, yeah. So this is case in discrete time. Okay. If you have question, just say it directly, yeah. Don't wait for me to ask you make a questions, yeah. Just go on, yeah. If you have questions. Okay, so we have nt plus 1 is equal to lambda times nt. Yeah. Let we make it step by step. Yeah. For example, at time 0, yeah, we will have a n0 individuals. Yeah. This is the initial populations. Yeah. Okay. At time 1, yeah, we will have a at time 1 we will have n. So this, I mean, t. So I have to emphasize it. Yeah. So n not here is given. Yeah. Given. Yeah. Provided by the data. Yeah. So we can start from t is equal to 0, for example. Yeah. So for t0 we will have n1, right? So n1 is equal to lambda times n0. Yeah. So at time 1, yeah, at time 1 we will have n1 is equal to lambda times n0. Yeah. Next, at time 2, we'll have n2 is equal to lambda times n1. Yeah. But n1 is equal to lambda times n0. Yeah. So we'll have lambda times lambda, which is equal to lambda squared n0. Okay, can you follow this? And etc. Yeah,
Yes,
and so on. Yeah, so at time t, we will have nt is equal to lambda times nt minus 1. And if we continue the process, yeah, so yeah, this one will be lambda times lambda and t minus 2. Yeah, is that correct? And then lambda times lambda again, and yeah, we make it in the square bracket, yeah, times minus 3, yeah, and so on, yeah, until it reach n naught. Yeah, can you imagine this? Yeah. So this one will be lambda squared. Yeah, this one will be lambda cubed. Yeah, etc. And then we, of course, I will have a lambda to the power of t. Yeah, lambda to the t, lambda pangkat t. Yeah. Okay, so we'll have nt here is equal to lambda times n naught. Yeah, individuals. Yeah. Okay, I have to delete this again. Yeah. Okay, so that's why, yeah, we will have general solutions for this. Yeah. So this is the equations. This is the recursion equations, and this is the solutions. Yeah, this is solutions of these equations. Yeah. Okay. So if you have, for example, n t plus 1, so we just replace t by t plus 1. So we'll have lambda times what? T plus 1. Yeah. Not time, to the power of time, to the power of t plus 1 times n 0. Yeah. Of course, that we can split it. Yeah. Lambda times lambda to the power of t times n naught. And this one is what? This one is nt. Yeah, nt. So this is consistent with this. Yeah, nt plus 1 is equal to lambda times nt. Okay, so this is the general solutions of this. So this is solution, and this is the equation. Yeah, so the solutions of this equation is this one. Ya, solusi dari persamaan ini adalah ini, gitu ya. Okay. Okay, let's see what happens to the solutions, yeah, to the expression of the solution of the recursion equations. Yeah, so we have nt is equal to lambda to the power of t times n naught. Yeah, let's say n naught is 5. Yeah, at the beginning, the populations of a species is 5 5 individuals, yeah, for example, this one. Of course, that the curve or the graph of these solutions depends on lambda, yeah. Let's calculate, for example, for lambda 1.1 first, yeah. Yeah, so you have lambda 1.1. So our next n, yeah, our next n at the next t, yeah, will be like this. Yeah. For example, if I want to calculate, so we have n naught is 5, yeah. So I want to calculate n1, example. What is the value of n1? Lambda is 1.1, yeah. So 1.1 times 1, yeah, to the power of 1 times what? Times so 1.1 times 5, yeah. So it will be 5.5, yeah. So this is 5.5, yeah. N2 is 1.1 to the power of 2 times 5. 1.1 squared. What is the value of 1.1 squared? 1.21, yeah. Is that correct? Times 5. What is the value of this one? 1.221 times 5. And can you calculate it in your, maybe in your mobile phone, maybe? 1.21 times 5. What is the value?
6.05, sir. 6.05, sir. 6.05.
0.5, yeah.
Yes, sir.
0.5. 6.05, yeah. So this is the 6.05, yeah. And so on, yeah. This is for lambda 1.1, yeah. And we can see that the number of populations with lambda 1.1 is increasing, yeah. Is increasing. Okay, that is for lambda 1.1. Let's try lambda is 1. Yeah, I have also another zoom. Yeah. Okay, 1, yeah. So 1, lambda is 1. Yeah, 1 to the power of any number is 1, right? Yeah. 1 to the power of 1, 1 to the power of 2, 1 to the power of 3, blah, 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 is always 1, right? So if we have n not in the beginning, so we'll have n not, yeah. In the next one, yeah, always n not, yeah. If we have lambda 1, yeah. So for lambda 1, we'll have this, yeah. Always 5, yeah. Or we can say it constant, yeah. It is constant, yeah, if we use lambda 1. Now, what about lambda is 0.9? Yeah, 0.9. You can try it, yeah. Just check it, just calculate it by yourself. So if you have lambda 0.9, so at t is 1, yeah, we'll have n1 is 0.9 to the power of 1, yeah, 0.9, right? Times 5, yeah. Of course, that is less than 5, yeah. Yeah, maybe 4 point something, yeah. And 2 is 0.9 times to the power of 2, so it will be 0.81 times 5, yeah. Of course, that it will less again, yeah, the number of n2, n3, n4, and blah blah blah. It will decrease, yeah. So increasing or decreasing of populations depend on lambda. Yeah. So what is lambda? Do you remember? Lambda is the
long wave, sir. Panjang gelombang, sir.
Don't make it a connection to other topics. Yeah, lambda is here. Yeah, we talk about lambda in this context, in this case. Yeah, so lambda is just constant. Yeah, constant that yeah, after we have made simplifications, right? First one, the births and the deaths. Yeah, we collect it and then we replace it by b by minus d, and then becomes r, and 1 plus r replaced by lambda. Yeah. Okay. Okay. Now let's try to calculate lambda. Yeah. Okay. Suppose we have this data. Yeah. So we have make records on the number of populations in this some species. Yeah, this is just example. Yeah. So at the beginning we have only one individuals, for example. Yeah. And then at time t is equal to 1, we have 5. Yeah, maybe t can be days, yeah, can be months, can be years. Yeah. At time 2, we have 35 and etc. Yeah, and so on. This is the data. Yeah, for example. Now, if we have this data, how can we calculate lambda in this case? Yeah. Okay, let us see this. Yeah, we rearrange, yeah, the equations. Yeah, before we have this one. Yeah, nt plus 1 is equal to lambda times nt. So we can rearrange this to get lambda. Yeah, lambda is equal to nt plus 1 divided by nt. Okay, do you understand this? Okay, now we can calculate our lambda in each interval of time. Yeah, in each t. Yeah, so lambda 1, for example. Yeah, if we have t if we have t 0. Yeah, so we'll have lambda is equal to n1 divided by n naught. Yeah, n0. So n1 is 5 and naught is 1. So 5 per 1 is 5. Yeah, this is for first lambda. Yeah. Second lambda is 35 divided by 5, yeah, which is equal to 7. Yeah. The third lambda is 80 divided by 35 is equal to 2.27. Yeah, and so on. Yeah, until we have lambda 5. Yeah, 1956 divided by 3 to 6. Yeah, which is 6. Okay, so we have some collections of lambda. Yeah, the values of lambda. Now we just simply take the average. Yeah, average of this. Yeah, what is the average of this? Yeah, we will have a point 4.87. the average, yeah, 5 plus 7 plus 2.29 plus 4 point blah 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 plus 6 divided by the number of this, yeah, 5, yeah. So it will give 4.87. This value will give us the estimate, yeah, estimate of lambda. Estimate of lambda. Yeah. Now, yeah, I will ask you, yeah, to draw, to plot, yeah, the graph of the model, yeah, with lambda is 4.87. Yeah, so I hope you can plot first this data, yeah, this data. It's very simple to plot it, yeah. You can use Excel, yeah, actually. So at 1, at 0, this is t, yeah. This is n and t. At 0, we have 1, yeah. At 1, we have 5. Yeah. At 2, we have 35, yeah, something here, yeah. And so on, yeah, and so on, and so on. Until 5, yeah. Just plot the data, yeah, into the graph. Now compare this, yeah, compare this data to the models, yeah. The models, yeah, our models, yeah. Our models is what? Yeah, the solution of our model is nt is equal to lambda to the power of t times n naught, right? Yeah, we obtained this before, yeah. So yeah, n naught we have the same value, yeah. N naught is also the same with this n naught, yeah. So it is 1, yeah, 1. So it will exactly at the same positions, yeah, between data and the model. Now, what about n1? According to our model, yeah, n1 with lambda 4.87, you have to make a power of t. T is 1, so will be, yeah, this one, yeah, this one again, 4.87 times n naught. N naught is 1, yeah. So n1 is 4.87, yeah, according to our model. So our model is actually somewhere under this point, yeah, because this point is 5, yeah, it's 25. So our model is, yeah, maybe something like this, yeah. N2, you can continue these calculations, yeah. Like T7 to the power of 2 times n naught. N naught is 1. Yeah, just calculate this, yeah. And so on until n5. Yeah, please calculate this, yeah. Just use Excel. I think everyone can use Excel, yeah. And then plot what you obtain, yeah? And then collect in one graph, yeah, so that we can compare, yeah, the data and the model. Can you understand what you should do? Yeah. Okay, yeah. But not right now, yeah. Yeah, after this, yeah, after this, yeah. Just keep it at the moment, yeah. Okay.
Like, sir.
Now we continue first to the exponential growth, but in continuous time. Yeah. What we have discussed before is in discrete time. Yeah. So we have only 1, yeah, 2, 3, 4, 5, yeah. But we cannot, we don't know between 1 and 2. What's the value of between 1 and 2, yeah? Between 2 and 3. So in this case, we need the continuous time. Okay, I think you have to try this first, yeah. Try this first. Make this first, yeah. I have to listen to the important part in the next Zoom. I also have another Zoom right now. Yeah. So maybe in 5 minutes, I think. Yeah. Try to calculate the models and then plot, yeah, into the data. Yeah. So we have two graphs. Yeah. The data and the models. Yeah. Can you do it? Yeah. In 5 minutes, and I will see your results. Yeah. Okay. Let do it. Yeah. Let's do it.
Right, sir.
Okay, have you finished? Hello, you finished?
On process, sir.
Okay. I think I have to continue this first. Yeah.
Right, sir.
Yeah. Just leave it at the moment, and then we will continue this explanation first. Yeah. Okay. Okay. So we will discuss about the exponential growth. Yeah, in continuous time. So basically it is just the same with the discrete time. Yeah. Now, yeah, we also have assumption that each individual reproduce. Yeah. Let's say the constant rate is this one. Yeah. B minus D. Yeah. This is just the same as the previous one. Yeah. So if there are n t individuals in the population at time t, then the rate of change of the whole populations will be this one. Yeah. The rate of change. Yeah. So how fast, yeah, or how quick, yeah, the change of populations. Yeah. This is what we mean by derivative. Yeah. Turunan. Yeah. I think you still remember about the explanations in mathematics. Yeah. In the first year, turunan. Yeah. We can make analog. Yeah. For example, with speed. For example, speed. Yeah. Kecepatan. So we have high speed. Yeah. It means that the positions of ourselves, yeah, in over time will be longer and longer. Yeah. Will be yeah, longer and longer. Yeah. If we have a high speed. Ya, kecepatannya tinggi misalnya gitu ya. Otherwise, if we have a low speed, ya, so it means that we will have a decreasing. Ya, the position will be will decrease. Ya, so that this is the same with the rate of change. Yeah, so if our rate of change is positive, yeah, positive, it means that we have a increasing number. Yeah. If we have a negative, it means that we have decreasing number. Yeah. I will make an illustration for this case. So for example, if you have a curve like this, so you know that if you have t here, so yes, this is our nt. So the gradient, yeah, do you know the gradient? Yeah, the gradient of this the slope, yeah, the slope, yeah, kemiringan, yeah, kemiringan. The slope of the tangent line, ya, garis misalnya garis I forgot about the terminology in Indonesia. So if we have a curve here, yeah, we have curves here. Garis singgung, ya, garis singgung, ya. Indonesia garis singgung, ya, this one. Yeah, you still remember with the concept garis singgung? Yeah, garis singgung, yeah. So if we have a curve here and then we pick one point, what is the garis singgung? What is the tangent line of this curve at position this one? Yeah, at this point. You know, yeah, the gradient, yeah, m, yeah. Actually, it is equal to dn over dt, ya, turunannya. Just remember about this? I think it is studied in the senior school, right? To find the gradient, yeah, we can find the first derivative of the curve, yeah, of the function. Yeah. So you can see here that the gradient is going up, yeah, because the curve is also increasing. So when the curve is going up, it means that the curve is increasing, yeah. Otherwise, if we have the curve going down, so our gradient is negative, yeah. It's negative, yeah. This is positive, this is negative. And this is negative, this is positive, yeah. So that what the meaning of the derivative here, yeah. So that's why we call it rate of change, yeah. So the change is just influenced, yeah, by this one, yeah, b times nt minus d times nt, yeah. So b is the rate for the birth, yeah, the newborn, yeah, the offsprings, and the d is the probability of dying, yeah, for species, and we make it b minus d is equal to r, yeah. Okay, can you follow this?
Yes, sir.
Yeah, so this is the differential equation, yeah, that I explained before, describing the rate of change of the population size, yeah, of the population size. Now, what is the solution of these differential equations? Yeah. Okay. Yeah. Let us recall this. Yeah. The ndt is equal to r times n. Yeah. Yeah. Now, we omit the writing t. Yeah. In this case. Yeah. Just make it simple in writing. Yeah. So this is just the same. Yeah. And t and n here is just the same. Yeah. But we didn't write t, yeah, in this case. Now, how to solve this? Okay, there are some methods. Yeah, there are some ways to solve the differential equations. Yeah, in mathematics we have some cases. Each case have a specific method. Yeah. Of course, that it will not enough time to explain all of the methods, yeah, all of the ways to solve the differential equations. Right now, I just explain, yeah, because this is just as one equations, yeah. I just explain one method, yeah, which is called separation method, yeah, separation method, yeah. Yeah, which means that we separate, yeah, the variables, yeah, which one have the same variables, yeah, into the different sides. So, example, here we have n and t, right? But here we also have n, so we replace or we move n in the left side, yeah, and we move dt into the right side, yeah. So if we move n into the left side, we will have 1 over n. If we have move dt to the right side, we will have a times dt, yeah, right? While r can be anywhere actually, yeah, can be right side or can be left side, yeah. because R is just constant. Yeah. But in this example, we put R in the right side, yeah, because I think it will be easy, yeah, to see, yeah. Okay, so from this step until this step, do you have a question? No? Does that
No,
understand?
sir.
No, sir.
Okay. Now, because we have the same variables in the each sides, yeah, so we can integrate. Now we meet with the integrations, yeah. I don't know whether in mathematics in the first year that you have learned about integrations. Have you learned about integrations in the mathematics course in the first year? Yeah, actually in the senior high school you have obtained this, yeah, integrations, yeah, integral, yeah. So yeah, we take the integrations in both sides, yeah, and then I think this is I don't know whether you have known this, yeah. So the integration of 1 over n respect to dn, yeah, respect to n is equal to ln, yeah, natural logarithm, yeah, ln nt. You know, do you understand why the integration of this is equal to this? No? Ida or anyone? Okay, I just make simple explanations, yeah. So if we have a function ln x, yeah, ln x, and x should be positive in this case, yeah, ln x. If you have calculators, you can try this, yeah. What is the curve of ln x? What is the graph? Yeah. So according to the calculus, or according to the mathematics, fundamental mathematics, yeah, the derivative of y is equal, the respect to x is equal to 1 over x, yeah, 1 over x. Okay. Okay, let us recall your memories about mathematics, yeah. If we have x squared, what is the derivative? Anyone? What is the derivative of x squared? Hello? X squared. What is the derivative of x squared? Two x, yeah? The power move on in the front of the x and 2 minus 1, yeah? Yeah. Okay. What about if you have x to the power of minus 1? What is dy dx? Anyone?
Minus x, sir, or per X. 1
Okay.
per X.
1 over X but minus. Yeah. So minus one, we bring it in the front of X, yeah, so it will be minus 1, yeah, minus 1, minus 1, yeah, minus 2. So it will be squared here, yeah, yeah, X minus 2 is 1 over X squared, right? Right? Okay. So in general, if you have X to the power of N, what is y dx?
And X.
And X to the power of N minus 1, yeah,
Yes, sir.
okay. Sorry. Yeah, I think you have to record this, yeah. Don't forget this. Yeah. Yeah. So if you have ln x, the derivative of this function is 1 over x. Yeah. Yeah. Okay. So if you have integration of 1 over x, it will be ln x. Yeah. So integration is just the inverse process. Yeah. Inverse process of the derivative. Yeah. Okay. So for example, if you have this case, yeah, 2x, integration of 2x, what is 2x? Integration of 2x, x squared. Yeah. But this without the boundary, ya, tidak ada batasnya, maka must be plus c, ya, some constant. Yeah. Okay, so this is the case, yeah, 1 over n. So the integration is ln n. Actually, this must be plus c, yeah, plus c. And integration of r dt, r dt as rt plus something c as well, yeah. Let's say this is c, yeah, c naught, this is c, yeah, c not something else, yeah. But this is constant, this is also constant. Let's say let's us collect them together, yeah. So let's say this is c1, yeah, all of them. So c1 accommodates, yeah, accommodate the constant integration of in the left side and also in the right side. Yeah, from this integration, do you understand? R dt is equal to RT plus C. Yeah, in this case, I write down C tilde. Yeah, you understand this?
Yes, sir.
Yeah. Okay. Okay. Nice. We continue. So yeah, this is slide 12. Yeah, we only have one more slide. Yeah. Okay. Now, from this step into next step, do you understand why we have this? You understand why we have this like this? Anyone?
Correct, sir.
Yeah, we have ln nt is equal to RT times C1. And then we can make it, yeah, nt is equal to E to the power of RT plus C1. You understand?
No, sir.
Okay. Okay, I will explain it briefly. So if we have ln x, yeah, for example, if we have y is equal to ln x, so it's just the same with x is equal to e to the power of y. Yeah, yeah. X equal to e to the power of y. E ya, bilangan e, tahu ya bilangan e, Euler ya, something 2.71 bla 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 lah gitu ya. The value of e. Yeah. So if we have in this case yeah, y ln x yeah, ln x is this one and t yeah, and this is y rt plus c1 yeah. Of course we have x and t is e to the y yeah? Y is rt plus c1 yeah. Do you understand about this? Can you follow? Yeah. If you have a calculators contains logarithm, natural functions, and exponential, you can check it. Yeah. For example, if you want to take the ln of 2, for example, yeah, ln of 2, yeah, just check it in your calculators. Do you have your calculators contains calculating ln in this case, ln and exponent yeah. In calculator we just use exp yeah, exp of what yeah. Yeah, if you have calculators like this, or you can also use R yeah, R Studio to calculate this yeah. Ln 2 is equal to what yeah. Then you can check it that 2 is equal to e to the power of something resulted in this one yeah. Okay yeah.
Sir.
Yes.
So the E is always 2.71, sir.
No.
Or
71 blah blah blah. Yeah. It is not a rational number. It is irrational number. Yeah. Means that the number itself will not have exact value. Yeah. We don't know. No one can knows the exact value of E. We just can predict it. We just can approximate it. Yeah. Yeah. This is just the same with pi. Yeah. Pi, you know pi? 3.14 blah 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 yeah. There is no one can obtain at the moment the decimal value of pi yeah. So if you want to stick it 3.14, you have to make it approximations in this case yeah. We have, if we want to stick 2.75, we have to make approximation of e yeah, not equals but approximate. Okay, Rika.
okay, sir.
Okay. Okay, now we continue. Yeah, this is yeah, I should explain this before actually, yeah, but we don't have enough time to see. Now we have a power, yeah, in this case. So we have if the power is in the summations, yeah, so we can split it yeah, into each of the power. Yeah, so we have e times 2 rt times e to the power of c1. Yeah, you understand about this? Okay. Now we can again simplify the expression of e to the power of c1. Yeah, we replace it by c2. Yeah, why? Because e is a constant. Yeah, yeah. Even though we don't know about the exact value, but it is constant. Yeah, and c1 is also constant. So constant times constant is also constant. Yeah. C2. Yeah. So we have nt is equal to e to the power of r times t times c2. Yeah, understood? Okay. Now we continue. Yeah. Now substituting t equals 0. Yeah. Why we have to substitute equals 0? Because we have the data and not. Yeah. And not is given. Yeah. And not is given, is provided. Yeah. We know this value. So if we substitute t is equal to 0, so n naught is equal to e to the power of r times 0, which is 1. Yeah. Because e times r times 0 is 0, right? So e to the power of 0 is 1. Yeah. Times c2. Yeah. What does it mean? It means the value of c2 is equal to the value of n naught. Yeah. So we can replace c2 by n naught. Yeah. So we have nt is equal to e to the power of rt, and c2 is n naught. So we just have now times n naught. Yeah. So the solutions of this, yeah, this is the differential equations. This is the solution. Ya, solusinya ini, gitu ya. I hope you can understand this ya. Oke ya. Oke. Anyone? Any questions so far? No? Okay. Now let us compare what we obtain in discrete time with the continuous time. In discrete time, we have this one, yeah. Sorry. In continuous time, we have this one, yeah. While in the discrete time, we have this one, yeah. But in this case, yeah, because they express the same expressions, yeah. So we can make a connections, yeah. We can make connections, yeah. So we now can make this one, e to the power of rt is equal to lambda power of t, yeah, yeah, because they have a quite the same, right? Same expressions, yeah. So e to the power of rt is equal to lambda of t, yeah. We know that if you have this power, it means that it was t times t, right? It was e to the power of r to the power of t, yeah. We'll have this one, yeah, r times t, lambda to the t, yeah. It means e to the power of r is equal to lambda. Right? Okay. Can you follow this? Yeah. So now we have a connections between lambda in the discrete time and r in the continuous time, yeah, which is given by these connections, yeah, these equations. Lambda is equal to e to the power of r. Okay. So if we have lambda, if you know lambda, of course that we will know r. Yeah. If you know lambda, we will know r. So for example, in the previous example, yeah, we know our lambda of 4.87, yeah. Do you still remember? Lambda 4.87, yeah, in the previous slide. So what is R in this case? How you can find R? So we can find R is just take a ln, yeah, just take a ln in the both side. Yeah. So this will be R ln E is equal to lambda, yeah, lambda, and ln E is equal to 1, yeah, ln E, yeah. So R is ln lambda. So if you have lambda, yeah, if you have lambda is equal to 4.87, so what will you have for R? Can you please calculate? If you lambda, so what is your R? R is lambda, is ln of 4.87. Please, can you use your calculator? What is ln 4.87? Do you have calculators? Or maybe you can use Excel as well. Yeah, you can use Excel. You can use any applications. Okay, you will share. Okay, I will share this first.
Hello, sir.
Yeah. Have you obtained?
No, the answer is 1.5x, sir.
1.
5x.
That is ln, yeah, not log, yeah. 1.5.
Yes, sir.
1.5 blah blah blah, yeah.
Yes, sir.
Okay, let us check it together. Wait. Oh, what's where's what's wrong with my laptop? Oops. Oh, oh sorry. Yeah. Okay, let us see together. Sorry, this is oh, I want to open Excel. 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 Okay, I will share this so that everyone can look at. What is ln? Ln of what? Ln of? Ini ya. Ln ya. Terus ini ln ya. Ln of 4.87 ya. Can you see my screen for Excel? Everyone? I think this must be 0, ya kalau di sini. Ah, ya. 1.583 3094 and blah blah blah, yeah. Okay, good. Now use this R, yeah. Use this value of R. Okay, I will share again the slide. Yeah. Yeah. Use this R. And now again, yeah, plot the third graph, yeah, for the continuous model. Yeah. What will you see? Yeah. So first you I told you that you should graph the data, yeah. The data, yeah, something like this, for example. Now plot the discrete model. Yeah, this is the same, yeah. Make a difference, make a different legend, yeah, make different types. Yeah, maybe something here, yeah, for X. And now make the plot for the continuous model. So the continuous model must be in the in form of curve, yeah. Should be in curve style, yeah. Yeah, for example, like this. Yeah. Yeah. So there are 3 plots that you have to plot it in one graph, yeah, in one picture. Okay, do you understand what I mean?
Yes, sir.
You understand what I mean? So in discrete time, you have this one, right? Lambda to the power of t and not, yeah. And in continuous time, you have e to the power of r times t and not, yeah. Okay. Lambda according to the data, yeah. Data we obtain, our lambda is 4.87, yeah. Yeah, this is discrete. This is continuous, yeah. And R we obtain before is 1.5 blah blah blah, yeah. 5.8, yeah. 5.8, 5.1, 5, yeah. Yeah. And not we obtain in the previous example is 1, yeah. Yeah, so just calculate this until 5, yeah, because we have a 5, right? The data, yeah. 1, 2, 3, 4, 5. Yeah, plot every value, yeah, of each time for discrete, and then plot the curve, yeah, because it's continue. Yeah, the continue must be in the curve, yeah, so that you will know, yeah, you will obtain what is the value of n at time, for example, 1.5, for example. We will know this, yeah. Oh, this one, yeah. So that's what is the difference between discrete and the continue. Okay, did you get it? Okay. This is your first task, yeah. Just make a plot for these different graphs, yeah. From the data, from the discrete model, and then from the continuous model. That's it, yeah. It's very easy actually. Okay, the last one. exponential growth, yeah, cannot, however, continue indefinitely. Yeah, we will not we will not be able to use this exponential growth for times bigger and bigger. Yeah, it only works for the short time at the beginning. Yeah, why? The reason is very simple. Yeah, suppose, yeah, we have, for example, pigeon. Yeah, the pigeon, burung pegar. Yeah, suppose that we have pigeon growth exponentially, for example. Yeah, at 1937, right? At the beginning, yeah. You can see, let us recall that. You can see the, yeah, this is our last slide, yeah. Okay, you can see here, 1938, and then 1942. If we continue this, yeah, according to the exponential growth, of course that will grow into the infinity, right? Sampai ke tahingga itu kan naiknya. Kalau kita ikuti modelnya model eksponensial, ya, baik di discrete maupun di continue. Ya, suppose, ya, for example, misalkan di tahun 1950, ya, maybe you will have 7 million individuals, 7 million birds, ya, 7 juta, ya, 50. And then let's say if you use this model, yeah, for example 2022, for example, yeah, maybe you will have 10 to 28. Yeah, 10 to 28 is more than, yeah. How can you say that? If we just make a simple calculation, for example, the mass of the pigeon, each of them is 2 kilos, for example, yeah. So 2 times 10 to the power of 28. This will be 3,000 times, yeah, of the mass of the Earth, yeah, which is impossible, right? It is impossible for the pigeon, yeah. The number of pigeon, the population of pigeon will be like this, yeah. In fact, right now, yeah, the pigeon itself not reach these populations, yeah. So this means that the exponential growth model is not realistic, yeah. It's not realistic, actually, yeah. It will be impossible that every individuals, yeah, every species will grows and grows, yeah, without the limitations, yeah. To fix this model, yeah, to repair this model, yeah, to repair the exponential growth, we will discuss in the next meeting that will be more realistic, yeah, will be more realistic model. That is the logistic growth model, yeah. So the model depends on the resources, yeah. It depends on the food, depends on the environment, yeah. Will not increase infinitely. Okay, that's all for these lectures, yeah. I hope you can understand. You can replay because we have record, yeah, this lecture, and then you can replay it if you want, and I will upload it in our iLearning, yeah. Okay, any questions, Rian? Yeah. Can you please on cam at the moment, Rian? Hello, Rian Maulana. Are you still there? Okay, no response. Okay. Okay. Any question, Yuda or Rika?
No, sir.
No, yeah. But you understand about the task, yeah? The assignment. Okay, just plot the figures, yeah? Just plot the graph of the discrete model and continuous model, yeah, that we have learned. Okay, so for the next meeting, when will we do it? Yeah. Do you have a time? Where's Yuda? Yuda is not here anymore.
Maybe his connection, sir.
Okay. Yeah. So we want to discuss. We want to make a deal with our replace schedule. Can we make it on Saturday? Saturday after one or after Zuhur, yeah. Do you have a class or do you have a schedule?
Online or offline, sir?
Yeah, of course, online. Yeah. Can you please come on cam your Zoom, please, Rian? Online because there is still one. I don't know. I forgot about the name. It sampai angke ya, right? Ya, oke, online aja. Ya.
Yes, sir.
Okay, Saturday. Anyone can do it after maybe 1:30, I think. Yeah,
I can, sir.
you can ya. Okay ya. Yuda, Rika.
I also can, sir.
Okay, good. Yeah. Okay ya. So we make a deal that Saturday will be our replace schedule at 1:30 by online. Yeah. And then please collect your assignment. Yeah. Each of you. Yeah. About the graph. Yeah. The graph of your calculations. Yeah. Okay. Yeah. That's it. We close the lecture. Yeah. Thank you very much for your attentions. And I'm sorry for all mistakes. We close by hamdalah. Alhamdulillah. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam, sir. Thank you, sir.